some key terms that you must first understand before proceeding to study the conductance of electricity. The first key term is electrical resistance, which has been given the symbol R. It is the opposition to the passage of an electric current. Resistance is measured in ohms. The SI base units for ohm are kilograms meters squared per second cubed into amperes squared. The electrical resistance of any object is directly proportional to its length, L, and inversely proportional to its cross-sectional area, A. We need a proportionality constant to turn this proportionality into equality. This proportionality constant is called resistivity or specific resistance and is represented by the Greek letter ρ. The SI unit for resistivity is ohm meter. Quite often, its submultiple, ohm centimeter, is also used. Remember that 1 ohm meter is equal to 100 ohm centimeters, or 1 ohm centimeter is equal to 0.01 ohm meters. If the length of the conductor is 1 meter and the area of its cross-section is 1 square meter, then resistance R becomes equal to the resistivity ρ. Thus, resistivity is defined as the resistance of a substance when it is 1 meter long and has a cross-sectional area of 1 square meter. Conductance, which has the symbol G, is the inverse of resistance. Thus, we can write that G is equal to 1 upon R. Since R is equal to ρ into length upon cross-sectional area, we can say that conductance is equal to area divided by ρ into length. The unit for conductance is the Siemens, which has been given the symbol S. Siemens is equal to ohm inverse or mho. The reciprocal of resistivity is known as conductivity. Conductivity is represented by the lowercase Greek letter kappa. Thus, we can write that kappa is equal to 1 upon ρ. We can substitute kappa in the equation we wrote a little while ago for conductance. Now we can write that G, conductance, is equal to kappa into cross-sectional area upon length. If the length of the conductor is 1 meter and the area of its cross-section is 1 square meter, then conductance becomes equal to kappa. Thus, conductivity is defined as the conductance of a material when it is 1 meter long and has a cross-sectional area of 1 square meter. The SI unit for conductivity is Siemens per meter. Sometimes, this is given as Siemens per centimeter. Note that 1 Siemens per centimeter is equal to 100 Siemens per meter. The magnitude of conductivity varies greatly, as shown in the table. It depends primarily on the nature of the material, although temperature and pressure can also affect conductivity. Depending on the magnitude of their conductivity, materials are classified into conductors, insulators, and semiconductors. Conductors are materials with large conductivities, such as metals and metal alloys. Some non-metals, including graphite, carbon black, and some organic polymers, also act as conductors. Insulators are materials with very low conductivity, such as glass and ceramics. Semiconductors have conductivities between conductors and insulators. These important electronic materials include silicon, doped silicon, and gallium arsenide. Apart from the three materials discussed, there are other special types of conductors known as superconductors. Superconductors have zero resistivity or infinite conductivity. The earliest materials identified as superconductors were metals and alloys at low temperatures, below 15 Kelvin. Certain ceramics and mixed oxides show superconductivity at temperatures as high as 150 Kelvin. Now let's discuss about the conductivity in metals, that is, metallic conductance. Metallic conductance, or electronic conductance, is the electrical conductance through metals. As the name indicates, the conductance is due to the flow of electrons in the metal. Metallic conductance depends on the nature and structure of the metal, the number of valence electrons per atom, and the temperature of the sample. Now, let's move on to the conductance in electrolytic solutions. You know that pure water exhibits conductivity, although it is very low. The concentration of hydrogen ions and hydroxyl ions in pure water is 10 to the power of -7 molar. Due to the presence of these ions in very low concentrations, pure water has a very low conductivity. When electrolytes are dissolved in water, ions are released into the solution. As the ions go into the solution, its conductivity increases. The conductance of electricity by ions present in a solution is called electrolytic conductance or ionic conductance. The conductivity of aqueous solutions depends on several factors, including the nature of the electrolyte, the size of the resulting ions, the solvation of the ions, the concentration of the electrolyte, and temperature. Directly measuring the conductivity of ionic solutions is problematic. Passing a direct current into an ionic solution changes the composition of the solution, as electrochemical reactions may occur. Also, unlike a solid conductor, such as a metal wire, we can't connect a solution to a Wheatstone bridge. To measure the conductivity of an ionic solution, we use a conductivity cell, like the one shown in the illustration here. A conductivity cell contains 2 platinum electrodes coated with platinum black, separated by a distance, L, with a cross-sectional area, A. An alternating current source is used as the source of power. The column of the solution separating the 2 electrodes then has a resistance described by the equation R is equal to rho into L upon A. The cell constant, G star, depends on the distance between the electrodes and their cross-sectional areas. G star is equal to L divided by A. The unit of cell constant is per centimeter. If we know the length and the area, we can calculate the cell constant directly. However, direct measurement of the length and area of cross-section of the electrodes are both difficult and unreliable. A better approach is to determine the cell constant by measuring the resistance of the cell when it contains a solution of known conductivity. For this purpose, we use potassium chloride solutions whose conductivity is known accurately at various concentrations and temperatures. The table here shows the conductivity of different concentrations of potassium chloride solution at 298 Kelvin. The cell constant, G star, is equal to resistance into conductivity of the solution. Once we know the cell constant, we can use it to measure the resistance or conductivity of any solution. To measure the conductivity, we can use a Wheatstone bridge. This device contains two resistances, labeled R3 and R4, and a variable resistance R1. The conductivity cell is the unknown resistance R2. The Wheatstone bridge is connected to an AC power supply and a suitable detector. When the bridge is balanced, no current flows through the detector. At these conditions, R2 is equal to R1 into R4 divided by R3. Inexpensive conductivity meters are commercially available and can also be used to measure the conductance or resistance of the solution in a cell. Once the cell constant and solution resistance are known, we can calculate the conductivity of the solution by dividing the cell constant by the resistance. The conductivity of different electrolytes in the same solvent and at a given temperature varies. This is because of variations in the charges and sizes of the resulting ions, the ion concentrations, and the ease of ion movement in the presence of a potential gradient. Therefore, we introduce the concept of molar conductivity, which uses a Greek letter lambda with a subscript m as its symbol. Molar conductivity is related to solution conductivity by the equation lambda m is equal to kappa, or conductivity divided by concentration of the solution. If concentration is expressed in moles per cubic meter and conductivity in Siemens per meter, then the unit for molar conductivity can be written as Siemens meter square per mole. To use molarity, which is a far more common concentration unit for chemists, we need to convert the units, resulting in the second equation given here. Let's work through a typical problem together. A conductivity cell is filled with 0.1 m KCl. The resistance of the KCl solution is 200 ohm. The same conductivity cell is filled with 0.03 m NaCl, and the cell resistance is 500 ohm. What is the conductivity and molar conductivity of 0.03 m NaCl? The conductivity of 0.1 m KCl solution is 1.29 Siemens per meter. Note that there are multiple parts to the problem. Here's our strategy. First, we need to find the cell constant, G star. We can do this by using the information given about the KCl solution. We know that G star is equal to conductivity multiplied by resistance. Given that the conductivity of a 0.1 molar potassium chloride solution is 1.29 Siemens per meter. Remember that Siemens is equal to inverse ohms. The resistance of the solution is measured to be 200 ohms. Therefore, the cell constant is the product of 1.29 times 200. The unit of ohms cancels, giving a cell constant of 258 inverse meters or 2.58 inverse centimeters. With the cell constant, we can now find the conductivity of the 0.03 molar sodium chloride solution. We know that conductivity is equal to the cell constant divided by the resistance of the solution, which has been given as 500 ohms. So, we calculate that the conductivity of the 0.03 molar NaCl solution is 0.516 Siemens per meter. We can use the equation shown here to find the molar conductivity from the conductivity and the molarity of the sodium chloride solution. By substituting and evaluating, we determine the molar conductivity to be 1.72 into 10 to the power 4 Siemens meters squared per mole. The conductivity and molar conductivity of an electrolyte change with the concentration of the electrolyte. As concentration decreases, conductivity decreases for both strong and weak electrolytes. This is because there are fewer ions per unit volume to carry current as the solution is diluted. However, molar conductivity increases as concentration decreases. The variation is different for strong electrolytes and weak electrolytes. Before we discuss the concentration dependence of molar conductivity, we must first understand the idea of limiting molar conductivity. This is the conductivity of a solution as its electrolyte concentration approaches zero. Limiting molar conductivity is given the symbol lambda m naught. The molar conductivity of strong electrolytes is weakly dependent on concentration. If we plot a graph of molar conductivity against the square root of concentration, we see that the y-intercept is the limiting molar concentration. The slope of the resulting line is the Kohlrausch coefficient, which depends on the specific salt. The Kohlrausch coefficient depends on the cation and anion charges of the ions formed by the electrolyte. You can classify electrolytes by the charges formed. For example, NaCl is considered to be a 1,1 electrolyte, since the sodium ion is +1 and the chloride ion is -1. Using similar reasoning, you can classify calcium chloride as a 2,1 electrolyte. Magnesium sulfate is a 2,2 electrolyte. All electrolytes of a particular type have the same Kohlrausch coefficient. Kohlrausch carried out studies on limiting molar conductivity for a variety of electrolytes. From his work, he deduced the law of independent migration of ions, or Kohlrausch's law. This law states that limiting molar conductivity can be represented as the sum of the individual contribution of the anions and cations of the electrolyte. For a salt of general form AYBZ at infinite dilution, limiting molar conductivity is equal to Y times the limiting molar conductivity of cation A plus Z times the limiting molar conductivity of anion B. Try to work through this problem on your own before checking the answer. Calculate the limiting molar conductivity for sodium sulfate from the data given here. Sodium sulfate contains 2 sodium ions and 1 sulfate ion. From Kohlrausch's law, the limiting molar conductivity is equal to 2 times the limiting molar conductivity of sodium ions plus the limiting molar conductivity of the sulfate ions. Substituting the values from the table, we get the limiting molar conductivity of sodium sulfate as 260.2 Siemens centimeter square per mole. The molar conductivity of a weak electrolyte depends greatly on the concentration of the solution. This is because weak electrolytes have a low degree of dissociation as concentration increases. Since the relationship isn't linear, we can't determine the limiting molar conductivity by extrapolating back to zero concentration. At infinite dilution, the electrolyte dissociates completely, but the conductivity is so low that it can't be measured directly. Instead, we can use Kohlrausch's law to find the limiting molar concentration. We can approximate the degree of dissociation, alpha, for a weak electrolyte as the ratio of molar conductivity to limiting molar conductivity. If the molar conductivity and the limiting molar conductivity known, then the dissociation constants for weak electrolytes at a given concentration can be found. Here is a typical problem. The conductivity of a weak acid in solution with a concentration of 0.002034 molar is 5.67 into 10 to the power minus 5 Siemens per centimeter. Calculate its dissociation constant if the limiting molar conductivity is 452 Siemens centimeter square per mole. Try to solve this problem on your own before checking the solution. First, find the molar conductivity using the equation you learned earlier. On substituting the values, we get the molar conductivity as 27.88 Siemens centimeter square per mole. Now, you can find the degree of dissociation for this weak acid, since you know that alpha, the degree of dissociation, is the ratio of molar conductivity and limiting molar conductivity. By substituting the values and simplifying, we get the degree of dissociation as 0.06168. With the value of the degree of dissociation in hand, we can use the equation relating Ka and alpha. Substituting the values, we get Ka is equal to 8.25 into 10 to the power minus 6